Today we are going to start with the latch up, and once we finish this latch up part, then we will also discuss the sequential logic circuits. Huh? So what is actually latch up? So before that, let us discuss, you already know the basic basic CMOS structure in terms of fabrication, right? And from there we will start and we will see like how these things has evolved, okay? And what do you mean by latch up and all these things. So we are not discussing what is latch up right at this moment, okay? So here you can see this is the diagram that I have already drawn here. So here this is the diagram of CMOS inverter, right? Because you can see this is what? This is NMOS, right? You can see this gate, oxide, P plus, P plus, this is N well. So this is NMOS, right? This is P silicon, right? This is N plus, this is N plus, right? This is oxide, this is gate. So this is what? This is PMOS, right? Because here, when you apply negative voltage, means with respect to source, then what will happen? Here, the charges will be induced, that whole like electrons would be induced here, right? And you haven't path from here. Are you getting my point? What I'm trying to say? Suppose, oh, oh, 1 minute. I think I need to restart this one. It is not writing. Not this one. Just a minute, huh? Could you please see that? Is it visible? Is my screen visible again? Those who are attending online.
Yes, sir.
Okay. Okay. So here you can see this is N plus, this is N plus, this is P silicon, right? So once you have applied positive voltage, that will induce this electron here, right? And that will form this NMOS, right? Similarly, you can see here, this is P plus, P plus, right? You apply here suitable voltage, for example, with respect to this source, right? Or with respect to N, that is negative voltage, that will induce here hole, right? And form this PMOS, right? Okay. So to make this PMOS, we have used this N well, right? It is a single well CMOS fabrication technique, right? Only one well. You could have also on P well here, right? But we are not using that for this technique. Say the technique is like the single well, only N well technique. Okay. So beside this, so this basically is the PMOS, right? This one is the PMOS. Beside that, we have one more implantation which is of N plus type, right? So this is what? Can you guess? This contact is for what? Similarly, what is this contact? Beside this N plus, there is an P plus contact. Body, this is obviously the body contact, right? So you can see here, this is N plus, this is N, right? So it is basically you are giving applied potential to this body terminal, right? And for normal configuration, generally we short this source and the body, right? That's what it has been done here for PMOS. Same thing has been done for here, right? For this NMOS, right? Okay. Now, if the structure is like this, then you have to make an inverter. So how does this inverter look like? PMOS, NMOS, inputs are connected, right? Are you getting this point? This is input, this is output. So inputs are shorted. So this is input, gate. These two are shorted. This is input. This output are these two connected. These two are output. Outputs are connected, right? Okay. Then this body is connected with VDD, so as this terminal. So you can see here. Similarly, this body is connected with this terminal. This body is connected with terminal, and it has been shorted. Means it has been grounded, right? Okay. So if the structure is like this, then let us see what is happening inside. Obviously, we have understood there is on PMOS and NMOS, but beside you can see, if you consider it like this is P plus, this is P plus region. So say it P, Okay, p region. Then this is n region, so it is p n, and then again you see there is an p region, right? So it is an n p n.
Sir,
So huh?
so can you please make the cursor bigger? We cannot follow.
uh, which part could you please mention?
No, sir, like when you say that this PMOS region or this N region, like since the cursor is not visible, we cannot follow like which P region or which N region you're talking about.
Oh, okay. Oh, cursor is very small. That's what you are saying.
Yes, sir,
Uh-huh.
like it's
Okay.
a dot
Okay.
and
Okay. Is
it's
it
like
better now?
yes,
Is it
sir,
better now?
somewhat. Yes, sir, it's better.
Or okay.
Thank you.
What about now?
Yes, sir, it's better.
Is it
Yes, sir, yes, sir. Thank you.
red? Okay. Is it better now?
Yes, sir.
Oh, okay. Fine. So here, what I was saying is that see, you have this P region, right? Then this is N well, right? This is N region, right? Below that you have P region. So that makes this P N P, right? So basically this forms that P N P bipolar. I mean, it's a type of, this bipolar, this structure is present here. Okay. Similarly, you see here you have this P plus, right? Okay, let us consider from here. This is N plus, this is N plus, please come. So N plus, right? Consider it as to be an N. This is P silicon. So it is P, so it is N, P. Then again here it is N well, right? So it is N, P, this is N, this is P, and this is N. So again it became N, P, N, right? So both PNP as well as NP transistors are simultaneously present. You can see in this CMOS inverter structure, right? Okay. Now let us try to understand it a little bit more. For example, you can see for this P plus, one terminal is connected with VDD. Okay, this one terminal is connected with VDD. Another terminal is connected with this output. Okay, that is also fine. Another terminal is connected with the output, right? This is N region. This is N region. That is also fine. But at the same time, this N region cannot be floating for a BJT. It should be have some terminal connect, right? So you can see this N is being shorted with this N plus, right? So there is a connection to this N region as well, right? Okay. Then let us come below. Then we have another P region here. Now this P region is being shorted with this P plus, right? When you have this P plus P, that means it is basically short. When you have an N and P, so that is basically an PN junction. So that is not a short, right? So here you can see N plus and between N plus and N, you have a short. Between this P plus and P, there is a short, right? So then basically you can see here, it clearly forms one P N P transistor, right? P terminals are connected, one terminal with VDD, other terminal with output, right? This emitter, this forms the emitter. The base terminal is connected with, again with VDD, right? Through a resistance. Why this resistance is there? Because this is N well. N well is not heavily doped. N plus is heavily doped, P plus is heavily doped, N is low dope. So when you have a low doping and the length is significant, then you have also some significant amount of resistance. So that is basically this resistance. So you have this N plus, through this resistance, it is connected with the base terminal, right? Now you see for this P, what is happening? Okay, this P terminal is this one, right? The entire thing is of this P silicon. The total thing is P silicon. But where is the PN junction? PN junction is this one, right? This is N and this part is P. Fine. Now, if suppose the the holes has been injected, right, and it has to then pass through the base. Are you getting my point? BJT action. The it is the PNP. Okay, or let me draw it here. Is it visible? Okay. So here you can see this is emitter, right? This is base, this is collector. So when you have forward bias, this emitter base junction, then what will happen? The holes will be injected and that has to pass through the base and then it will be collected by this collector terminal, right? See here what is happening. This is VDD and suppose we are able to make this PN junction forward bias, then the holes will be injected from here, then it will come to the N well that is in the base region. Then from this base region, it will be collected by this P region, which is the collector, right? So now it has been collected by this collector region. Now this collector region is also P silicon, which is also not heavily doped. So this path, if the hole has to reach, then this hole has to be collected by this P terminal only, right? Then the hole has to travel up to this much path. So obviously this will also face some resistance through this path. So this is that resistance R substrate. So is it clear why there will be an N well, this resistance which is indicated as Rn well, and there will be another resistance which is of R substrate, right? Then you might argue then why we are not considering the resistances inside this. Yeah, if you want to make an accurate calculation, you should also consider the resistances of this P plus region. But as these regions are heavily doped, so for the time being, we could have neglect that resistance. Okay. So then this formation of PNP, this resistance is clear to you. Now let us see from the this side. Okay, here you have N plus, here you have N plus. That forms the emitter terminal of this NPN junction, right? Again, see one terminal connected with the output, other terminal is grounded, right? Okay. Then this P silicon forms the base, right? And this P silicon is again connected with this, right? Okay. Then you should have one more region which is of N type. So here this entire region is of that N type, right? And this entire region is connected with N plus region, okay, through this. Is it clear? Then the formation of these two transistors and how these resistances are coming. Okay. This clear, right? And basically, if you now try to rethink about this, that entire circuit, then probably you can also understand from here, you could have probably draw an equivalent circuit model like this. For example, if you can compare these two, it would be great. So this is VDD. Okay, let me put it like this. This is VDD. So with this VDD, this is VDD. With this VDD, you have this P plus region. You have this P plus region, right? Then another P region is connected with the output. So this is another P region. So this is connected with the output, right? Then you have this N region. This N region, this N region is being connected with what? This N region is being connected with this resistance Rn well. This N region is connected with an resistance Rn well, right? And Rn well is being connected with VDD. So Rn well is being connected with VDD. Fine, this part, okay. Now let us come back to this. So here we should have one more, this is PNP, one more P region. So this is that P region. Now this P region is connected through one resistance R substrate to ground, right? So this is that P region through R substrate, it is now connected with ground. It is now connected with ground, right? Okay. Now let us come and to this, and let us see that whether we can explain it from here or not. So this is N region, these two are N region. One of the region is connected with the output, other region is grounded. So you can see one of the N region is already grounded, other is connected with the output. So this is connected with the output, right? Okay. Then what about the base region? Base is P plus region. Sorry, base is this P region, and this P region is connected through a resistance R substrate to this, which is actually grounded. So this P region through R substrate connected with the ground, right? Okay. And you have this collector region. The collector region will formed by this N plus or this N region and this N plus region, and this collector is connected with this VDD. So you can see here this collector through a resistance R N well through a resistance R N well, this collector is connected with the VDD, right? So you can simply, if you want to model it, because for some electrical analysis or for simulation, because electrically you cannot simulate this, right? You need some RC transistor combination to simulate it, right? So that will be the circuit for electrical simulations, right? Okay. Now let us focus only this structure. Okay, the highlighted regions.
Sir,
Okay. Huh.
sir,
Yes.
so where is the input connected?
Where is the input connected? Inputs are always connected with the gate of the MOSFETs, right? These inputs are not connected with any of the parasitic BJTs, right? Okay. So if you now consider this one, okay, the highlighted regions, that basically is the circuit representation of a device which is called SCR, okay, silicon control rectifier or thyristor, right? Silicon control rectifier or thyristor. If you have not studied thyristor so far, then we can see what is the basic structure of thyristor, and then after that we will come back to this discussion again. Fine. So let us understand what is then SCR or thyristor. Yes. So this thyristor or silicon control rectifier is a four-layer structure of different like PN structure. Diode is an two-term, like diode is an only PN. BJT is of this PNP or NPN, like sandwich of three semiconductors, whereas this thyristor is a sandwich of four different semiconductors. So you can see here PN. This P terminal, the top one is called A, which A stands for anode. This N terminal, which is in the bottom, is called cathode. To represent it in the circuit, we generally give K. K stands for this cathode. And we have a gate terminal, which is connected with this P region, right? Okay. Now let us try to understand how this circuit or how this device will behave when you apply some voltage very briefly. Okay. For example, let's say that for the time being, we have grounded this cathode. Hmm? Anode means, always you have to apply some positive voltage to the anode. Cathode means negative voltage. So we are saying grounded. Negative voltage means relative, right? Negative does not mean the magnitude should be negative. It's compared to it's always the potential is always relative, right? So here, suppose you have applied a positive voltage. And for the time being, let us say no voltage has been applied to the gate terminal. So gate is type of floating, right? Okay. When you have applied positive voltage here to this anode, what will happen to this PN junction? This PN junction is in forward bias. Do you agree with me? This PN junction is forward bias. What about this PN junction? This is also forward bias, right? What about this PN junction? This is in reverse bias, right? And so, and you also know from the property of this PN junction, when you apply reverse bias, mostly all the voltage that you apply will be drop across the reverse bias junction. If you just neglect the, that 0.7 voltage drop across that, then mostly all other voltage would be applied across this PN junction, right? So mostly whatever the voltage you are applying, say VA, would be applied across this reverse bias, right? Okay. Now, if you further increase it and say when you have applied VA, nothing is happening. You are getting a very less current from here anode to cathode, which is very low. It would be the leakage current, right? Between this reverse bias PN junction. Now, suppose you are increasing VA, then what will happen? Probably nothing will happen much. If your increase in VA is very small, if you are increasing VA to a quite large extent, then what will happen? Then this is reverse bias PN junction, not heavily doped. So there is a possibility of breakdown. So breakdown occurs in two mechanisms: Zener breakdown, avalanche breakdown. Avalanche breakdown occurs for a lightly doped, primarily for the lightly doped PN junction. Zener breakdown occurs for heavily doped PN junction. That's why for Zener breakdown, generally the breakdown voltage is pretty small, right? So here say these regions are not that heavily doped, okay, then what will happen? Avalanche breakdown or avalanche multiplication will start come into the picture, and this PN junction, which is reverse bias, will start leaking, right? So whatever be the current through this, the same current has to flow from this anode to cathode, right? Then what will happen? Your conduction will start. Your conduction will start from anode to cathode, right? Even if this junction is reverse bias, right? And once the conduction has started, okay, once the conduction has started, then probably the requirement of voltage to this VA is no longer very high. Are you getting my point? Please try to understand this point. Once the conduction has started, then probably you can reduce this VA to a lower magnitude, because avalanche multiplication has already started. So that, right? Avalanche multiplication has already started. That means you have lots of carrier here, right? And this will keep on, like once the multiplication has started, it is type of, this ice, this on top of what is called that iceberg, what, that on top of these hills. I'm
No
for,
caps.
huh?
No caps.
Yeah. Suppose you have some, right, frozen ice right here in this avalanche. Yeah, this is called, that is called avalanche only, because see, if suppose by some means you are able to just push it little bit, right? Then after that, what will happen? This much push would be enough to make like everything to be collapsed, right? You don't need any further force, right, to sustain that avalanche process. That's what I'm trying to say, right? Once this avalanche has started, probably you could have reduced this VA. No longer you don't need any further like force to continue that, right? Okay. By the way, this is an not even ice actually. This looks something. Okay. So you understood. So what is going to happen if you do not have here, say, even any gate voltage? Okay. Now let us try to understand this, okay, from another perspective. That is, this anode cathode gate terminal is fine. Now we can break this PNPN structure into like this PNP, right? And we can also break this structure like this. Oh, I think while drawing this one only, you try to point it out, right? This is NPN. What is the difference between thyristor and two diodes in a series? Okay. So, right, two diodes in a series back to back, like this. Right, right. Here you see what is happening. Okay, is there, like, there is a junction here which is an NP, this PN junction, right? Is there any, okay, let me write it again here, this PN. Is there any junction between these two? No, is there any, okay, why it is not there? Okay. Then probably let us take it like this, consider it like this. PN, then let us take some metal. Okay, so this is metal, this is metal, this is metal, right? So basically the structure become, this is metal to semiconductor, this is become semiconductor to metal, this M is for metal. Okay, so this become N metal, then P. So this is not a PN junction. So obviously, if you consider these two PN junction connected in series, that is not the equivalent of a thyristor or SCR, right? So this PNP, so this four layer structure probably can be represented like this. The PNP, this NPN, right? Where these two ends are same. So basically they are shorted. These two P are same. So basically they are shorted, right? And you have the gate terminal here, right? So I can write it like this. Because why we are doing this? Because if you want to correlate with because we want to correlate this device with one of our known structure, right? So this structure looks known to us, which is an PNP bipolar junction transistor. So as this is an NPN bipolar junction transistor. So you can see if we can represent it like this structure, then we could have also say that equivalent circuit of this is like this, right? Right. Now, are you getting some correlation between this and the previous page diagram where we have seen this? Right? These two are now correlated. So basically then this one, the yellow highlighted region is basically the SCR structure or thyristor structure. All right. So how this circuit or how the IV characteristics of this SCR would look like, right? Let us try to understand that. So here we are plotting I and this is the V. V is what? V is the voltage between anode and cathode, right? Say gate is now floating, gate is floating. Then what will happen? Say we have keep increasing this voltage. Then what, right? Slowly this current will increase. Initially the current will be very small because the current will be due to the reverse saturation current, right? Ideally this reverse saturation current should be constant, but practically for diode, if you do, it will not be constant. With increasing voltage, reverse bias voltage, it will increase. So slowly you will see that it will also increase, right? And at a certain point or a certain voltage, this avalanche process will start, carrier multiplication, right? At that point, so this is that point, triggering point. Then immediately what will happen? Immediately there will be lot of carrier, right? And you need lot of voltage here, like lot of voltage, almost all the voltage will be dropping across this, right? But when this junction will be started leaking means there will be huge amount of current from this from this N side to P side. Then what will happen to the voltage drop to this region? That voltage drop will significantly reduce. You are you getting my point? So like for example, when you have an diode operating in the breakdown, what is the resistance across that diode? It is basically type of short. So right, very small voltage drop across this diode. Then what will happen to the voltage between this cathode and anode? That voltage also have to be dropped because you need only this junction to be forward bias, this junction to be forward bias. The voltage across this dias is significantly low, right? Then all of a sudden the voltage that you have applied will now drop to this much. All of a sudden voltage, once you reach this point, after that there will be a sudden drop in the voltage, right? Are you getting my point? After that, if you further increase this V, then what will happen? The current will start rising very, very sharply. Because now it is almost a short device. Fine? Okay. Now, that's what, initially I said. Once this avalanche has been triggered, then you do not need that high voltage to sustain it. You can get a very high current by applying a very small amount of voltage across it, right? Then what is the purpose of using this gate terminal? Okay, so in this gate terminal, if you say like okay, suppose this gate terminal, we are applying some positive voltage, right? Then what will happen? Initially this junction, okay, let's say this gate terminal we are applying positive voltage. This junction was reverse bias earlier, right? But now we are applying additional voltage to this P. So that means we are trying to make this PN junction forward bias, right? So the avalanche, which was earlier possible at a higher anode voltage, that avalanche will occur at much lower voltage, right? So what will happen? You can see from here, if you have in higher gate voltage, that means in terms of current, you have an higher current, then this traceback will occur at much lower voltage, right? After this, immediately it will start like this, right? Now, if you further increase this gate voltage, or in terms of current, if further increase the current, then that current would look something like, right? So by applying this gate voltage, you can reduce what would be the triggering voltage for this SCR or this thyristor, right? This is the purpose. And remember one thing, once you are operating in this region, you don't need any further voltage in this gate terminal. You could have completely removed the gate voltage from here because the avalanche has triggered. The sole purpose of this gate voltage was just for triggering that avalanche process. Once it is triggered, you don't, no longer this gate voltage is required, right? Okay, now the question is, okay, we understood how to turn it on, but how to turn it off, right? Because a device is not like we'll be happy to turn it on, right? We have to also intentionally, so we have to switch it off, right? This device can be turned off if you apply, suppose, a negative voltage to this gate by making that PN junction reverse bias, or you drop or you make this voltage V below this level. Okay, there is a voltage level which is called this one. This is the holding voltage VH. If you reduce that below this, the device, right, this potential is no longer supportive for that avalanche mechanism, so the device will turn off, right? So I hope this gives a brief idea about SCR, right? And let us now try to implement this knowledge in CMOS latch-up. Let us then again come back to this. Right. I think I have drawn one more set of diagram here. Yeah. Right. Then let us now come back to this latch-up process again. Okay. With the same diagram. Now, you see, this for this latch-up to start, what we have to do here? Okay. Let us try to understand one of the scenario first. If you understand the scenario first, then the other process would be clear to you. Say, for some reason, there isn't some spike in VDD. VDD is what? VDD is the supply voltage, right? There might be some spike in VDD, and say that spike is greater than 0.7 volt. Basically, it's you have to forward bias this PN junction, right, to switch this on. So for that, there should be some voltage, some voltage spike which is greater than this PN junction turn-in voltage, right? So suppose you have that spike, and say couple of assumptions. Say this Rn well is very large, so as R substrate. So very large, these two, Rn and R well. So if there is a sudden spike, then that spike will immediately influence this PN junction, right? By forcing this, by forcing this PN junction to be forward biased, right? Okay. Then what is this? There is another, this is P, this is N, this is P, right? This is what? This is P is already connected with the ground, right? And this N is already connected with some of the positive voltage, right? So that makes this PN junction reverse bias, right? That's why this terminal will behave as these two terminal will behave as an base and this collector terminal, right? These two terminals are already reverse bias, right? So what we have to do, we have to just momentarily for a certain, for some time, you have to just forward bias this. So if we are able to forward bias this region, then what will happen to the collector current? IC, say IC1. IC1 will increase. Okay. If IC1 increase, what will happen to this IE1? IE1 will also increase. Okay. If IE1 increase, what will happen? IE1 will try to create a big voltage drop across this, right? Okay. But we said this is already very high, right? So current will always try for the lower resistance path. So it will see that I have also one more path, which is IB1, IB2. Say this is transistor Q2, this is transistor Q1. Okay, so I have one more path, right? So then it will try to increase this IB2. Once this IB2 will increase, what will happen to this IC2? IC2, it will increase, right? If this IC2 increase, then from some region IC2 has to flow, right? Okay, again, can it flow through this RN? Well, yeah, some part, but it will try to find, some other path as well. So it will try to see that there is one alternative path which is from here, which is IB1, right? So it will try to grab as much as current from this IB1 as well. So that will result the increase in this IB1. If IB1 increases, that will further increase IC1. If IC1 increases, that will increase IE1. IE1 increases, that will again increase IB2. IB2 increases, that will again increase IC2, right? That will again increase IB1, and the whole process would be repeated, right? So basically there is a positive, this positive feedback, right? There is a positive feedback in this, right? And this positive feedback will keep on continuing until and unless this process stops or the device get damaged, right? Okay, do you agree with my point? Should I repeat it? No. Okay, so you understand that there is a positive feedback, and as a result of this positive feedback, what is going to happen? A huge amount of current, will be flowing from VDD to ground. Do you agree? A huge amount of current will be flowing from this, because the current has to flow from this VDD only ultimately, right? And to ultimate terminal, I mean between this VDD and this ground only, right? The current has to flow, right? So if this happens, then what will, if the current is very high, then what can you say about the resistance? That means you can say the resistance between these two has reduced drastically, or eventually we can say this VDD and this ground will eventually be shorted, right? So this is one of the destructive situation. We do not want this to happen, right? But if you see the construction of this CMOS inverter or any CMOS logic, then you can see due to the presence of this parasitic bipolar junction transistor, right? One parasitic SCR operation comes into the picture, or thyristor operation comes into the picture, and as a result, what will happen? The device is prone to malfunction, even destruction, right? This device can get permanently damaged, right? Yes. So any doubt so far? Okay. Now then, let us try to understand briefly what are the causes for this latch up, right? One thing obviously with that we have discussed, that sudden spike in supply rails. Supply rails means it is VDD and ground rail, right? So far we have discussed from the point of view of VDD only. The same situation can also be explained in terms of ground, because if you come back to this, then see here, this is the base to emitter junction, right? If this ground potential, okay, has gone below by 0.7 volt, right, by some spike, then what will happen? This makes this PN junction forward bias, that will increase this IC2, this IC2 will increase IB1, then again the whole scenario will again come into the picture, right? So you could have, right, like latch up could have occurred because of that, because of the sudden increase in sudden spike in VDD as well as in the ground, right? So any rail sudden spike, that you can create the latch up issue in an CMOS inverter, right? Okay, now we are saying that there might be sudden spike because of the supply rails, right? like, can you think of some practical reason why this spike might be possible? Huh? Can you speak loudly? Huh? Rectifier. Yeah, but why there might be sudden spike in, oh, rectifier. Okay. Yeah, rectifier is fine, but there might be other reasons, say like electrostatic discharge, right? You are turning, huh? During switching, very good. During switching, it can happen, right? So all of a sudden, if you are turning off all the devices, then there might be a spike. For some, it is not be, it will, the spike will not sustain for a very long time, but it will be for a very small time, and that would be enough for triggering this latch up action. The second one is ESD, that is electrostatic discharge, right? So you have some terminal like electrically isolated, right? But like type of, what you have seen in terms of this during thundering, right? So basically it is type of one this electrostatic discharge only, right? Between two static charges, if the gap is low, right, then there might be a breakdown of this intermediate dielectric, and all of a sudden there will be a huge amount of charge flow from one uh, electrode to the another electrode, which will cause an momentarily sudden amount of current, right? That is also possible in semiconductor ICs. Okay. Other than that, X-ray, gamma radiation, this can also play a major role. For example, if you try to understand it from here, it would be better. Suppose this junction is reverse bias. No, this junction is not suppose. This is always reverse bias. If you apply here positive and here negative, right? This is reverse bias. But if you radiate here this X-ray or gamma ray, then what will happen? Do you know what is the effect of radiation on semiconductor? It will create lot of excess carriers. Means electron hole pairs would be generated simultaneously, right? So previous, and that might create, and avalanche operation similar to the avalanche operation here, right? So again, for momentarily, means for all of a sudden, due to creation of lot of additional charges, you could have also seen and latch up operation, right? So these are the primary three reasons for this latch up. Now, if you have understood this latch up, then we should also discuss something regarding its prevention. We cannot see bhai ye hota hai to chhod do, right? So we have to do something to prevent it. Okay, so how to prevent this latch up, right? First thing is that why this latch up is happening, why there is a positive feedback. Can you comment on that? Why there is a positive feedback? Because of low resistance path, that is fine. Because of low resistance path, there is a positive feedback. No, the low resistance path is the result of positive feedback. But why there isn't positive feedback, or what should be the criteria of having this positive feedback? Say the gain of this transistor is beta 1 and the gain of this transistor is beta 2, right? So for every cycle, the carrier generation or this beta 1 and beta 2 has to be greater than 1, right? Then only it will sustain that loop. Otherwise it will break it, right? If there is no amplification of this charge carriers, right, then that whole thing would die, right? Then if by some means you can break this relation, that is beta 1 beta 2, you can lower the value of this beta 1 and beta 2, then you could have also reduced the latch up issue. Now the question is, how can you do that? How can you reduce the beta of a transistor, bipolar junction transistor? What will happen if you increase the base doping? Base doping will reduce beta, right? So for example, for this, if you increase this N-well doping, that will reduce the beta. There are a couple of other ways. One is this by reducing the, increasing the doping of this. Could you please check, is it still? Sorry. Those who are online, can you still see my screen? Can you still see my screen?
Yes, sir.
Okay, thank you. Okay. So, yeah. So what you have to do, you have to increase the doping, right? Other way would be you need to reduce the injection efficiency. Injection efficiency also will decrease if you increase this ND. What else? How can you reduce this injection efficiency of a bipolar junction transistor? By reducing the doping of this P plus or the emitter region. Remember injection efficiency, or you forgot? Forgot. Huh? No, injection efficiency was gamma. It is not alpha. Alpha is the like IC by IE. Alpha is the current gain. Injection efficiency is what? Suppose if you have a bipolar junction transistor, emitter, base, collector, then suppose n number of, or suppose you have n number of electrons has been emitted from here, right? And what is the number of electrons captured by this collector, right? So injection efficiency maximum value can be 1, right? Because if you can capture all n numbers, that would be injection efficiency is the highest. If there is some recombination in the base region, injection efficiency will drop, right? So to have a higher value of beta, you have to make injection efficiency as high as possible. But here our intention is to reduce the injection efficiency, the opposite requirement. So we have to either reduce, we have to increase this, we have to reduce this. But when you reduce this, what will happen? This will create an parasitic resistance for the MOS. Okay. So if you reduce the doping in this region or in this region, then what will happen? That will increase an parasitic resistance for the MOSFET. That is not intended. So you cannot reduce it. So one technique is called you can use it Schottky, instead of this ohmic contact, you use some Schottky contact here. So if you use them Schottky contact, that will reduce this, that will reduce this gamma, and basically that will also reduce this beta, right? So there are a couple of techniques. The techniques that you have studied for increasing the beta in gamma value or injection value in your semiconductor device courses, you need to apply the same logic here for reducing the value of parasitic beta, the beta of this parasitic bipolar junction transistor, right? Yes, very good. So one suggestion is, can we insulate these two transistors? Then probably we would be able to isolate these two parasitic transistors. Yes, that is the technique that is actually already been used. So here, the first thing we have to use is an buried oxide. So you can see here, buried oxide means underneath oxide. So you use an underneath oxide layer, right? And you use also this trench oxide. This trench oxide we have already discussed regarding the device isolation part, right? How to isolate PMOS and NMOS by using the trench isolation. So that is the same technique, trench isolation. So you use trench oxide here, right? Trench oxide here, right? So you can see here, then this basically this gives what? This makes the PMOS. This makes NMOS. कि भाई नींद आ रहा है क्या? Okay, so here it is P plus, here it is P plus, it is N plus, it is N plus, right? So basically we are able to isolate this PMOS and this NMOS from each other, right? Then one of you might suggest, earlier the whole issue was because here you have an N plus contact, body contact, but here you are not giving any body contact. How so or why so? Then okay, no issue. We can make here an N plus region, make it a body contact, right? Even you see that parasitic bipolar junction transistor is not coming into the picture, right? You have only this N plus and N region. The parasitic region is not coming, right? For parasitic bipolar junction transistor to come into the picture, you need NPN, 3 layers, right? So this is one technique. The other technique is called this use of guard ring. Okay, use of okay. So use of guard ring. So here what is typically been done, say like if you okay, let me draw it here. This P plus, this P plus, this is one terminal, this is another terminal, this is oxide, this is the gate terminal, this is one of the terminal. Okay, it is source, this is drain, and this is N silicon, right? And you have one N plus region here, right? If I look it from the top, if I look it from the top, then how does it look like? Top view. It would look something like this. You have this P plus region. You have this P plus region. This is P plus, right? You have this gate region overlapped. This is the gate region, right? And you have this N plus region for this body contact, right? Top view would look something like this, right? Here we are going to introduce one more layer, or not one more layer, one more doping, okay, which is called a guard ring doping. So we are going to introduce here, you see, this is an what type of transistor? This is an PMOS. So for PMOS, we have to use an P plus guard ring. So we will use a guard ring of here P plus and here P plus. So how does that look from the top view? From the top view, that would look something like this. It is a ring, basically, you know. Right? Have you understood? We are going to create this P plus region, or this P plus region is called this guard ring regions. Okay, around this. How does this guard ring will help? Okay, let's see that. If you have this, if this is the emitter, right? You can see from here the previous one. For this, this and this two would be the emitter, right? Okay. So you see for here, if this is emitter and if this is injecting an hole, right? This guard ring is connected with this guard ring is connected with a ground, right? This is hole, this is a P plus region and has been connected with a ground, right? This hole will be attracted to the like lower potential compared to this. All these holes will go and would be taken care by this guard ring. Means it will capture that, right? Are you getting my point? So the action which has triggered the latch up operation, that can be prevented by using this type of guard ring. So this P plus guard ring around NMOS and this P plus guard ring, just let me confirm one thing. P plus guard ring should be connected with ground, okay, and N plus guard ring, N plus guard ring would be given across this NMOS, and N plus guard ring has to be connected with VDD, right? Has to be connected with VDD so that the injected electrons would be captured by that guard ring only, right? That way you can prevent the latch up operation. Huh? Huh. Right. Yeah, I think, yeah, there is a small correction here. Okay. So, yeah, there is a good that you have noticed this. There is a small correction. So it should be N plus guard ring. Okay. Why it is N plus guard ring? Okay. Let me just rectify this one. This is N plus guard ring. This is N plus guard ring. See why N plus guard ring is required. This is grounded. If it is P, then that basically forms PN junction with this, right? That will again do some type of reverse biasing, this one, reverse biasing or forward biasing, this PN junction. So around this, you have to use this N plus guard ring only, so that it makes a ohmic contact with N plus and N region, right? So, and whatever the injected holes are there, that would be collected by this N plus regions only. So have you understood? Do you have any doubt? Okay, na? Huh. P plus guard ring around NMOS. Actually, I am this. There is in one more. It was here. Small space, insert space. Increase the height. So I was actually running out of space. So I thought that. Okay. So if there is any confusion for this PMOS, so this is PMOS, right? For this NMOS, the structure would be like this, na? N plus, right? And you have gate, you have source, you have drain. Then what we are saying, for NMOS, you have P plus region, you have P plus region, and P plus regions are connected with VDD because, okay, you have another here P plus region. This is connected with the body, right? Isn't it? So that's how you can actually prevent the latch up. So yeah, any doubt so far? Okay, then can we take 1 or 2 minutes break and then start the sequential logic circuit? Okay, so those who are attending offline, so you might think why I have made the screen like this, right? Why not full screen? Okay, so I will show you what will happen if I do that. You understand? We can reduce the size. Okay, so this view zoom say 50%. Okay, so this view zoom say 85%. But that also probably makes the same thing, right? Because if when it has been recorded, this region will also, the side region will also be recorded, right? So rather, if I make it like this, huh? If I make it like this and make the zoom say 100, not 100%. Actually, there is an option called page width. Yes, page width. Then what will happen? Like only this part would be recorded because I am sharing only this much. Hey, is my screen still visible? Okay, so then can we start? We have to like finish quickly. Yes, and I hope that I am still recording it. Yeah, I am still recording it. Right. So, so I am still recording it, right? This is still recorded, no? Record. Okay. Okay. So then let us start quickly this sequential logic circuit. So far what we have discussed is mostly towards on the understanding or implementation of the combinational circuit, right? By using CMOS, right? But in sequential, in sequential logic circuit, you already know that, right? It is basically a combination of combinational logic plus one memory element, right? Memory element in the feedback, so that the output of this sequential circuit will not only dependent on the input alone, but also it will dependent on the previous output or outputs, right? Okay. So let us with this, with this objective in our mind, so let us start. But again, the building block is the inverter. Okay, so let us again start from the inverter. So this is a normal inverter, say implemented using CMOS. We have discussed it, so there should not be any doubt. So if I now ask plot it VTC, then you can plot the VTC in should be within 1 minute, not 1 minute. 1 minute is too long, right? Maybe within few seconds, right? You should be able to plot the VTC. The VTC should be like this. Okay. So here it is the V input 1 and here it is V output 1. No doubt. Okay. Then let us also draw one more inverter beside that. Okay. And say here the input is VI2 and the output is VO2. So I must segregate this and this from this. Okay, this is for this part and this is for this. Right. So for this, how the VTC will look like? Again, same, right? Same inverter, say the same size. So the in VTC would look something like this, right? It is VO2 versus VI2, no doubt. Now, I'm saying something here. I want to connect this, right? Then VO1 become equal to VI2, right? Okay. So And one more thing, I want to plot these two VTC in a single plot like this, right? Then you see this is V naught 1. V naught 1 is equal same as V naught was as is same as that of VI2, right? So that means we have to push this axis, like take this axis here and take this axis here, right? If I do that, then probably how does that would look like? So it will be VO2, and here it will be V what? VI 2, right? It would be VI2. So how does that look like? Probably it will look something like this, right? It is look something like this. Okay. Now we can say like these two are same, right? These two are same, right? Fine. But again, this is I1 and this is O2. These two are different, right? These two are different, right? These and these are still different. But now what we are saying, let us do one thing. Let us also connect these, right? So that makes VO2 equal to VI1, right? So that way now this equal to this equal to this. Then we can superimpose these two VTC on a single plot, right? Okay. So here we have already written V naught 1 equal to V in 2 and V in 1 equal to V naught 2, right? Then these two plot, right? These two plot will have to be superimposed and you will get a VTC something like this, right? Okay. Then these two inverter, these two and like if you see the characteristics of these two inverters, then they intersect in these 3 points, right? One is this A, other one is say like this point is B, and the third one is say C, right? So there might be then 3 solutions, right? Like from here, either it can be here or it can be here or it can be here, right? Okay. But say, what is this V in 1, right? What is this V in 1? Let me just see it one also one. What how I have planned. Okay, that would help me in discussing this. Okay, so here this is V in 1, right? So V in 1 is this one. This is V in 1. Oh, here I think I have written VI1. So please try to please understand I and in are same. Okay, V in is same as VI. Okay. Okay. So if by some means, suppose you change or you try to set this value, this V in, say to exactly to this value. Say this is VDD by 2, symmetric inverter, right? So you make VDD here. Okay, give VDD here, right? So that will give the output VDD by 2, same output, right? Again VDD by 2 for input for this, so that will give VDD by 2 as the output. Then that is again feeding back here. So VDD by 2, right? So it will be, then the loop is sustained, right? But say if we say VDD by 2, then we cannot say like it is exactly at VDD by 2. It might be say VDD is 3, then VDD by 2 is exactly 1.5. If I say there is some noise, say even in the millivolt range, so there will be some perturbation. Okay, say noise in the positive side or negative side. Let us say for the time being negative side. Say the noise is little bit, can make this point little bit shift to this, right? Then this is now the input, right? That will create a output here. It will create, again be reflected. You remember the first type of the first class that we have done, reflected here, then it will be again reflecting here. So basically if you have small perturbation even from this point C, which is one of the solution, then either you will go and end up with point A or you will go and end up at in point B. right? There is no valid point or no stable point between this A and B. Are you getting my point? It should be either A or B. So these two are called this stable states. This one is the metastable. That you can give it. It's possible theoretically, right? But due to some noise, eventually we will either end up with to go with point A or with point B, right? So then from this we can say one thing. If we connect two inverters like this, right? Then there are only two stable operating points, A and B, right? And see, A and B stands for what? Either if you see from input side, it stands for either 0 or VDD. So that means logic 0 or logic 1. So in terms of logic, so what I can say, the stable point is only the logic 0 or logic 1, or in terms of this voltage, I can say it is only the 0 volt or this VDD. This is the stable point, right? Okay. Now say I have given or applied a and trigger, say triggering pulse. Okay, triggering pulse here. Okay, whose logic is 1. Logic 1 means VDD. Say I have given a logic of means a pulse, triggering pulse with certain time duration, and the amplitude of the pulse is VDD. So then basically I have given here 1, right? So that will force the output to be equal to 0, right? If this is 0, that will force the next output to be equal to 1. If this is 1, then this is in feedback, right, with 1, right? Then if I remove it, means after applying the pulse, I have stopped applying the pulse. Then what will happen, you see, this total circuit will will act as a memory, right? Because it will remember that, okay, what was the previous pulse? I have given pulse 1, so it will remember that pulse 1, right? Until and unless you disrupt the power supply, right? Suppose if for this, what do you mean by power supply? If you think from the circuit point of view, then to make this inverter, right? To make this inverter, you need VDD, right? So if you cut the supply voltage VDD, then that information will be lost. Are you getting my point? So as long as the power is there, you have given trigger, so that will also act as a memory, and it can store only 1 bit, right? Okay. Now suppose it is storing 1 bit, you can say, remember, okay. Now I want to overwrite it. I want to write a 0. Then what I have to do? Send a pulse of what magnitude?
0.
Send a pulse of 0.
No, sir. I mean, give 0 input for a while, for a short while, and then it will remember.
Right. So that means you should have also some triggering pulse application in between, right? Now you have to apply and 0. So basically you are forcing this to go to 0 when you, and that is true for a certain duration, right? For certain duration you have to apply that pulse, right? Because this has to propagate here, then this has to propagate to the next one, then only it will remember. If you disrupt that supply or disrupt that impulse before that, then what will happen? Then it is not going to. Okay, I think all those things we will discuss in the next class. Yeah. Means there should be some time for which the input to be valid, right? If you interrupt the input before that, then you might get something wrong in the output. Okay, so if you now given a impulse of 0, like a pulse of 0, then what will happen? That will force this output to go to 1. If this 1, then it will force to go to 0. And then after that, if you remove the pulse also, then it will remember that 0 bit. So it will remember 0 bit. So then we have understood that a basic arrangement by this into inverter can act as an memory and can store 1 bit. We'll come to that. Yes, you could have, we will see that applications. These two, basically they are represented like this. They are used in many places. Now, there are two types of memories, static memory and the other one is the dynamic memory. So we'll discuss bit later on. Okay, come to the discussion bit later on. Okay. So basically, this is the circuit, right, that we have discussed. This will act as a memory. And it is also called the bistable circuit because it has only two stable states. Now, if you think from the circuit transistor implementation point of view, then the circuit is basically like this, right? So this output is act as an input to this, and this output is acting as an input to this, right? Okay. Now, again, to just to focus on this bistability principle here, then suppose if you have given some voltage here Vm and due to noise there is some perturbation, then with respect to time, right, this perturbation will change and this Vm will approach to Vh or the same thing what we have discussed just to represent it graphically or to this VL. Either it will approach to VL or VH, right, after certain amount of time, right? Yes. Now, before starting this SR latch and all these things, so let us discuss at least one thing. So what is the difference between latch and register? Forgot? Digital, no? One clock? No, it's not with the clock. Yes, it is with the label and edge. Okay. These latches are label sensitive. Label sensitive. So that means if you have a clock pulse or if you have an input like this, then this would be sensitive. Then this latches would be sensitive to this region, right? Okay. Rather than if it is register, then register is basically age sensitive. So if it is for register, then for register it is these two that will play the major role. Either it is the positive edge or the negative edge, depending on how you have designed your circuit. Right? Then let me ask you one thing. What is flip-flop is an edge triggered or flip-flop is an level triggered? Flip-flop can be both. It can be both edge triggered, it can be both the level triggered. So there might be one confusion there. Okay. So that's why many places we will try to not write, SR flip-flop. We will write SR latch just to say that this circuit should be sensitive to the level, not to the edge. Okay. Then the basic memory, SR latch. Then the question is, so far we have seen that these two inverter connected like this will also act as a memory, right? This also act as a memory. This can store 1 bit. This can also store 1 bit. Then why we need this SR latch and all this latch? To improve mechanism. What type of which by mechanism say? Right. We cannot, we do not have the provision for recalling what is the memory and all these things for here. But those provisions are possible for SR, JK, all these latches, right? So this SR latch, you know, it can be implemented by NOR gate. It can be implemented by NAND gate. So suppose we are implementing by using NOR gate. So it is NOR implementation. NOR implementation. If you are implementing using NOR gate, then the circuit would look like this. Do you agree or disagree with me? This is SR latch. Okay. What would be the characteristics table, which is basically a modified version of or truth table only, right? Okay. What would be the truth table for this or characteristic table for this? When you apply 0, 1, the output would be 0. If this is 0, then this is will be 1. When it is 1, 0, this would be 1, 0. When it is 0, 0, it will remember the previous state, right? So that's what I am writing it like Qn and Qn plus 1. N plus 1 is the present state, N is the previous state. Okay. What about this one, 1, 1? That is interesting. Here is the race condition, right? Because it depends on which one reaches first, and eventually we'll end up with both this Qn and Qn plus 1 to be equal to 0 and 0, which violates this our notation that this Qn plus 1 and Qn plus 1 bar should be the output. So the same output cannot be there here. So this is that not allowed would inputs, right, for SR latch, right? So it is this part you already know. No, you right already. Okay. Now let us see its CMOS implementation part of this. So what is the big deal? If you know the circuit, you know how to implement NOR gate to input NOR gate, and the connection already you know, then you can implement it. No big deal, right? Okay. So here would be this, right? You see this this one. This is that NOR gate, right? Two input NOR gate. Here, this is the two input NOR gate, right? For this NOR gate, one of the input is S. So you see this one of the input is S. The other input is this Q. The other input is Q. You see this is Q. This is the other input, right? Yeah, any doubt? Okay. So so this is the other input, and this is the other input. S other input is this. So similarly, if you notice for this one input is R, the other input is this Q bar, right? That basically makes this circuit or implementation of this circuit in CMOS, right? Okay. But yes. So can we do a quick check, right? Whether like the truth table that we have made here that is been followed in this circuit or not, right? That is required. So let's say any combination which is valid, say 0, 1 combination. So S0, R is 1. So when you have S0, that makes this transistor off, this transistor on, this is 1, this transistor off, it makes this transistor on. So now you can see this Q point is connected with, already connected with ground. So obviously this has to go to 0, right? Now this is 0. Now this has been fed to this transistor as well as this transistor, right? This 0 make this transistor off, make this transistor on, right? So now you can see there is a direct path from VDD to this Q bar, which will charge Q bar, charge it to 1, right? And this Q bar is now driving this, right? So Q bar is 1, that will make this transistor off, that make this transistor is on. So anyway, this point is already been connected with the ground through this.
Sir,
So now we have one more connection. Yes, please.
Sir, again the cursor thing, sir.
Huh?
The cursor thing, sir. The cursor is very very small.
Oh, okay, okay, okay. Cursor, I am
Yes,
forgetting.
sir.
Okay, okay, right. So, right. So, okay. Then, suppose for zero input, this transistor is off, this transistor is on, right? For input one, this transistor is off, right? This transistor is on. So, as this transistor is on, this terminal is already connected with the ground. So, obviously, then this point would become go to the ground level. Now, this zero is driving this PMOS. This PMOS then has to be on. Then you see this point Q bar is already connected through these two PMOS with this VDD. So this Q bar is charged, Q bar will rise to VDD. So that means 1. This Q bar is driving these two transistors. So that makes this NMOS on, this PMOS off, right? So that makes this for 0 1 combination the output become 0 and 1. So see, for 0 1 combination the output become 0 and 1. So this is valid, right? So similarly you can cross check it for 1 0. I am not doing it. Okay. Now let's say after this input only we have applied the other input, that is the next input, that is this one, 0 0, and let's see that whether it can recall the previous state or not. So now we have applied 0 0. So let us take another color. So now we have applied 0. Here also we have applied 0. So when you have applied 0, that makes this transistor on, right? This transistor on. That makes this transistor also on. Both this transistor on, right? Okay. This makes this transistor off. This makes this transistor off, right? So now clearly you see this Q point, this point, point Q or the point Q bar is not directly connected to any of the ground. Neither you can say it is connected with the VDD at this point, because to connect with VDD, you should have this transistor also on, this transistor to be on. To connect this VDD, you should have this transistor to be on, right? We do not know that. Similarly, it is not connected with ground as well, because this is off, this transistor is already off, this transistor is already off, and we do not know the status of these two transistors. So we can comment what would be the value of this Q and Q bar, right? Here comes the previous state. So because already we have to now see what was the charge that is stored here, or what was the voltage that this Q was holding earlier. So earlier Q was holding the 0 value. So that makes this transistor on, that makes this transistor on, right? And this transistor off. The Q bar was holding 1. So this Q bar would make this transistor off and this transistor on, right? So now you can see this point Q have a direct path with the ground, right? It has a direct path with ground now, right? And similarly, you can see this VDD has a now direct path with this Q bar. So that means the output will remain at 1 and 0 for this case, right? So if you apply this 0 0, then it will recall the previous state. Now, if you want to check whether it's for 1 1, what is happening, we can also do that. Say, like we have applied here 1, we have applied here 1. So when you have applied 1, then what is happening to this? This transistor is on. What is happening to this? This transistor is already on. So that means both Q and Q bar is connected with the ground. So that makes this Q bar and Q bar both equal to 0 and 0. It does not matter what is the condition for this, like top PMOS status or the pull-up network status, right? So that way you can check. Is this part clear to you? Okay. Then we could have also implement this SR latch using NAND gate, right? Okay. So this is the implementation. Means the implementation means this is the like gate level diagram. Okay. So remember, this is called gate level diagrams. This is called circuit or transistor level diagram. Right? Transistor level diagram, gate level diagram. Okay. So here when you have S and R and you are using NAND gate, so earlier with S you are getting Q bar. See, with S you are getting Q bar. I hope you know that, right? But for this implementation and NAND implementation, this it would be Q and this would be Q, right? So similarly, then can you not fill this truth table? So here for 0 1 it would be 1 0, it would be 0 1, this would be Qn, this would be Qn bar, and here this state would be equal to 1 1, and this is not an valid input for SR latch. 1 1 is not the valid input for SR latch, right? So then the question is, do I need to explain the same implementation again? No. Can you explain by yourself for 0 1 what is happening to which transistor is on, which transistor is off? You can. Can you tabulate it? Tabulate means suppose if I have to give name like M1, M2, M3, M4, M5, M6, M7, M8. Can you make a table like this? Say M1, M2, M3, dot, 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 M8, and say for SR equal to 0, 1. Can you make this is like right on, off, on, something like that? Can you make a table like that? If you can do by tick and cross, obviously, why not in a table, right? So this is the tabulation part. Okay. So if you want to tabulate it, okay. Like this. Is it but clear to you? Nothing fancy here. Right. Now the getting bored, huh? Okay. So now one so far what we have discussed here in the sequential circuit, everything we have discussed in terms of CMOS logic, right? But we know that we can make inverter, we can make NAND gate, we can make NOR gate by some other ways as well. For example, there are other techniques, resistive load inverter, right? By using the resistive load, you can make NAND gate, NOR gate, any gate you can make. Similarly, there is a technique called pseudo NMOS technique, right? Where the load is basically this one PMOS whose gate is grounded, right? So this is the pseudo NMOS technique, right? So in this technique, this is what. So this is which logic? This is pseudo. This circuit is representing one logic in pseudo NMOS. Why? Inverter. Why are you taking so long? See, this is inverter. You apply 0, you will get here 1. You apply here 1, you will get here 0. Right? This is an inverter. Right? Okay. Now suppose you want to implement SR latch. Okay. Using NOR. Right? Then from the gate level diagram, we know that NOR implementation can be done by like this. If you want to implement this SR latch. Right? Okay. Now, how do you represent NOR gate in pseudo NMOS? How do you represent NMOS in pseudo? How do you represent NOR gate in pseudo NMOS? Pull down network would be the same, right? So very good. So here it is this. So it is V. Yeah. Now please tell me what should I do? Two parallel combinations, right? Okay. This is A, B, ground, right? Here this F is equal to A not B. Isn't it? Right? So if we can implement any logic function, then you should be also able to make latch with this, right? So let us see that how to do that. Can I go down? Okay. So let us see that. This is the latch representation. Okay. If you are getting any difficulty, then probably I will do it like this. A, B. Now please check with this. Is it valid? This is what one NOR gate. This is what another NOR gate, right? This NOR gate, okay, for this NOR gate, the output is Q bar. This output is Q bar. This Q bar should be the input for the next another NOR gate. So this is the input for the another NOR gate, right? And here for this NOR gate, this is the output, and this output is driving the other NOR gate, right? Then if I ask you, can you implement SR latch using NAND? Yes, right? In pseudo NMOS logic. If I ask you use with enhancement load, can you do that? Same, right? If you can make inverter, you can make any logic. When you can make any logic, you can also make latches using that technology. However, as you know, this transistor is always on, right? This transistor is always on, right? So whenever this is on or this is on or both are on, there will be a direct path. There will be a direct path from VDD to ground. So that will create lot of power dissipation even in the statics, even in the standby condition. Means if you are fixed at one, even at that point also, it will create lot of power dissipation, right? Okay. Please give the date. Is this part clear to you using SR latch? Now, it is clock SR latch. Because so far, if you do not have a clock input, then what will happen? Any change, any change here, or let me go back to here. Any change for this inverter, sorry, for this SR latch, if there is some momentary noise, that can also affect this output, right? Any change in this input will immediately impact the output. But, and also it is not been synchronized, this part with the other part of the network. So if you want to synchronize and say like I only want the output to be changed only when the clock is high. So that way you can synchronize it with the rest part of the circuit. So how can you do that? By using a clock SR latch. So what is the funda of this clock SR latch? The funda is that before that you make an arrangement like this. You make an arrangement like this, right? Okay. Just give me 1 or 2 minutes, or that would be it's fine. Okay. So this is SR latch. So the additional part is this one only. Remaining is this the NOR implementation, right? Here it is clock, here it is S, and here it is R, right? So how can you now implement it? See here what is basically Q. So what is basically here you are getting? It is S dot S and clock. And what is this and here it is Q. This is Q. So what is then Q bar? Q bar is basically S clock plus Q whole bar. Isn't it? Right? So how can you implement it in a circuit? See, it's very simple like this. So you have S. So you have S, right? You have here Q. Q is coming to this, right? You have clock here. You have clock here. Okay, as you have exam, okay, like from 12 o'clock, right? So maybe we can end here now, and we'll start this discussion from in the next class. Okay, but please give a thought on this, that whether this circuit is working or not as a clocked SR latch. Fine. Okay then. Thank you. So I thought of completing multiplexer based latch, latches using transmission gate, pass transistor, master slave, flip flop, all this. So anyway, not able to complete. Thank you.